Hi everybody, Professor Rad here, and today we're going to talk about division with decimals. So we're going to do two examples of using the long division algorithm to express answers of division in decimal format instead of as quotient remainder form. The one key that we're going to use to help us do this is the fact that any number has infinitely many unnecessary zeros off to the right after a decimal point. So for example, if I have the number 32, I could think of that as 32.0 or 32.0000. I can just keep adding zeros however long I want or need to, and I'm still going to have the same number. Let's work through example A here and see why that's going to be important when we go to find decimal results. So 32 divided by 5 says we're going to put 32 into the box and 5 on the outside. Now I'm going to use my 5 times tables for this, which I have memorized, but you could also use repeated subtraction or write out the 5 multiplication table if that helps you. 3 is too small for 5 to go into, so I'm going to say how many times does 5 go into 32? And the closest we can get is 6, because 6 times 5 is 30. So we did our going into question, we did our times, now we do a subtract, and we bring down the 2. Well, we get 2 when we subtract. Now, because they want us to give our answer in decimal form instead of quotient remainder, I have to keep going until one of two things happens. Either I end up getting 0 after I subtracted, or I notice something fishy going on. I notice a pattern that's going to continue to repeat. So I didn't get 0 when I subtracted here, and we're too soon to find any pattern. So I'm going to add a decimal point and a 0 so that I have a digit that I can bring down. And now I repeat my long division process. Before I do that, since I added the decimal point here, let me toss it up top as well. We want to make sure everything's nice and lined up. So now, how many times does 5 go into 20? Well, 5 goes into 20 4 times, exactly, because 4 times 5 is 20. And when I subtract, I get nothing left. So that means 32 divided by 5 in decimal form is going to be 6.4. Let's check that on the calculator. So if I do 32 and I divide that by 5, in decimal form, we get 6.4. Yes. Okay, so let's do another one. We've got 1.6, and we're going to divide that by 9. 1.6 goes in the box, and 9 goes on the outside. Now, one thing that's a little strange, even though 9 is bigger than 1, certainly bigger than 1.6, it doesn't matter which of these two numbers is bigger or smaller. The first one always goes inside the box. The second one goes on the outside. And that's because if we're getting decimal answers, you can get a decimal answer of 0 point something, which is actually what's going to happen here. Because 1 is too small for 9 to go into. So I'm going to put a 0 there kind of as a placeholder. And I'm going to look at this as if it were 16. So I pretend this decimal's not here when I do the going into question. It's just here, sort of, I kind of place it and then forget it, really. Set it and forget it, right? So kind of like when we did the traditional method of multiplying with decimals, the decimal point only really had an impact towards the end. Here it just has an impact that I have to remember to write it and line it up. Now, again, I'm going to use my 9 times tables to do this, but again, you could use your fingers, the little trick for 9s, or you can write a 9 times table or use repeated subtraction. But I know 9 is going to go into 16 only once. And if I do 16 take away 9, that's going to give me 7. Oh, excuse me. So, I didn't get 0 here. And again, we're too soon to see a pattern. So I'm going to add a 0 that I can then bring down. 9 goes into 70 7 times, because 7 times 9 is 63. Then I'm going to subtract, and I didn't get 0. So I'm going to add a 0, bring it down. 9 goes into 70 7 times, because 7 times 9 is 63. Going to subtract that, and I get 7. So I didn't get 0, so I'm going to add a 0 and bring it down. 9 goes into 70 7 times. Excuse me. 7 times 9 is 63. This is looking really repetitive now. Oh my goodness, excuse me. I'm noticing that I had a 70 minus 63, 70 minus 63, 70 minus 63. Next, I'm going to have a 70, and it'll be minus 63. And so since all I'm adding are zeros forever, I'm going to keep getting this 70 minus 63 forever. So this is how repeating decimals are formed. We end up getting this pattern that 7 is going to keep going on forever. So 1.6 divided by 9 is going to be 0.17 with a line over the 7. Let's check that on the calculator. Let's see what this one says when we do that dividing. 1.6 divided by 9, and look at that. It tells me 0.17 with a line over the 7. I'm going to bring in another calculator that gives me the answer in a slightly worse way. Yeah, I said it, slightly worse way. Just so we can see what will happen. So I'm going to do 1.6 divided by 9. And here you can see this calculator says 0.1, a whole bunch of 7s, and an 8. So the reason it's putting this 8 here is not because it knows something we don't know. It's putting this 8 here because this calculator is like, I'm not going to go on forever. I'm going to stop when I'm tired. And since the next digit afterwards would be a 7, that means the 7 would round up to an 8. So when you see repeating digits on a calculator followed by the next digit up, chances are that means your calculator's rounding the answer. All right, so here are a couple of questions for you to try. Use the long division algorithm to find each quotient and give your answer in decimal form. In our next video, we're going to wrap up section 2E, or chapter 2E, by doing sort of a similar thing that we did with multiplication. We're going to do sort of a reasonableness check of whether a quotient should be larger or smaller, depending on what we divide it by. So I look forward to seeing you then, and in the meantime, I hope you have a wonderful day. Bye for now.